go over linked lists more later, so don't worry too much about what's in this. The main thing is a linked list consists of nodes. A node has two parts, a data and one or more links to the other nodes. The data could be anything. It could be a scalar, it could be a composite. In most of the examples in the book, it's just an integer. A linked list looks something like this conceptually. Okay, the header to the list usually is a node itself. It may or may not be, though. It could just be a variable that contains the link. The first one that has real data in it is a node. It has some sort of data, which again could be composite or scalar. Atomic is what the book is using instead of scalar. And then it has a link to another node, which has a link to another node, and so on. On a linked list, you always have a head and you have a tail. You may or may not store where the tail is, but you do always have a head for the linked list. Okay, so a node is a structure, has two parts, the data and one or more links. Nodes in a linked list are self-referential, which means they contain one or more pointers to other instances of the same structural type, in this case a node. A node in a linear list is going to have one link in it. A node to a nonlinear list might have more than one link. There's such a thing as pointer to void. C is strongly typed, and operations that assign and compare must be compatible types or cast to compatible types. The one exception is the pointer to void. It can be assigned without being cast. It's a generic pointer. It can be used to represent any data type during compilation or runtime. Now, a pointer to void is not the same thing as a null pointer. It's pointing to a generic data type, which in this case is called void. Okay, this demonstrates a pointer to void. We've got void and star. Star means it's a pointer type. And P, so P is a pointer to void. Now if we set P to the address of I, then we can print the contents using P. And so we would have to say, we can't just say to print star P, because P is a pointer to void here. So we have to tell it what the data type is. If we had said int star here, then we wouldn't need to say int star down here. We would just say star P. Okay? But since it is a pointer to void, we have to cast it as a data type int star. Then we can dereference it with the star. I will go over the concept of pointers in a separate video. Hopefully you remember from C that you can call malloc and get this will allocate a chunk of data for you, or chunk of memory for you. And so if you want to create an integer dynamically, you need to know how big that integer is. So you say size of int. That'll give you how many bytes an integer takes up. And then you're going to call malloc. Okay, that returns a pointer to void. Now, if you want it to be a specific data type, which it's best to do, then you put what kind of pointer it is in front, cast it. Remember, casting is in parens in front of the item. So then say int star, and then so now if you dereference int pointer, it will be of type int. Okay, if you didn't do this, then you would have to, every time you used it, you'd have to come up here and do it like that, like you did for P here. That's a pain, so don't do that. Do this instead. Here's a little chunk of code. It creates a node in dynamic memory and stores data pointer in it. Okay, so we've got our node, type def struct node, and we've got void star data pointer, and then struct node star link, and then it's of type, we're going to call that node. It's traditional to have your types as all caps. Create node is going to return a pointer to type node. Okay, so it's going to return node star. And you're going to pass it a pointer, which is going to be of type pointer to void, or void star. So you say node star, node pointer. Okay, so node pointer is going to be a pointer to type node. And then node pointer equal, we're going to malloc it the size of node, so that's how much memory we're going to get back. And then we're going to cast it to node star. And then we're going to take the node pointer, its data pointer is going to be set to item pointer, which we were passed, and then its link is going to be set to null because it doesn't point to anything itself yet. And then we're going to return node pointer. By the way, this was our header file, so it's a .h file. Okay, so we're going to include p1-02.h. That was the header file above. Okay. Then we have our int main void, and we're going to have int star new data, int star node data, and then node star node. New data is going to be, we're going to dynamically allocate it with malloc. It's the size of int, so it's going to hold an integer and return it as an int star. Then we're going to set new data to 7, and since it's a pointer, we have to dereference it first by putting a star in front of it, and I'll tell you more about that in the other video. And then we're going to say node equal, and we're going to call create node, the one we just did a minute ago, and pass it new data. Then node data equal, and we're going to take our node and its pointer, which is data pointer, and convert that, cast it into an int star. And then if we want to print the data from the node, then we'd dereference it, say star data, star node data. If this is all clear as mud, don't worry about it yet. We're going to go over it again on the section on linear lists. And if you don't remember anything about pointers and stuff, watch the other video on pointers that I'll be presenting. Okay, ADT structures usually have several instances of a node. If you just have one, there's no point in having it at all. You just put it into a scalar variable and forget it. Okay, then they've got the code if you have two nodes that are linked together. Okay, I'll let you run through that. We'll go through more of this kind of thing in the linked list chapter. Okay, there's such a thing as a pointer to a function. I wish they hadn't put that in this chapter. That's really kind of complicated. The idea is not complicated. Actually doing it's complicated. Pointer to a function, also known as function pointers. Remember that everything gets loaded into memory, right? Your variables are in memory. We think about that a lot. But we don't really think about the fact that our program gets loaded into memory too. But it does. Our program is in memory. You send it to the compiler, it compiles it into machine code, and then when we run it, it puts that machine code in memory. So anything that's in memory is going to have a memory address, right? So a pointer to a function is simply, it knows where that function is in memory. So that place has a pointer, right? It has an address, so you can put it into a pointer. So that's what a function pointer is. What you do with it is a little more complex. Okay, as we saw in our discussion of pointers to void, we place our generic function, which we call larger, in a header file so it can be easily used. The program interfaces and pointers are shown in figure 113. Okay, so here's the beginning of the function called larger. It returns pointer to void, and the name of it is larger. Its first parameter is a pointer to void, data pointer 1, and then its second parameter is a pointer to void called data pointer 2, and then we're passing it this thing. This is a function, okay? Pointer to CMP fun. And then it has a star in front of it, means it's a pointer. And then this is actually a prototype, okay, like you'd put at the top of your code. And so it's going to have two void pointers as parameters. And then the whole thing is of type integer. Sorry, every time I click on anything, the whole thing does weird things. Okay, so if this third parameter is greater than 0, remember it's an integer, so we can compare it to 0. I know it doesn't look like an integer, but it is because it says int right there. Then you return data pointer 1, else return data pointer 2. Okay, so here's main. Okay, we've got our includes, this is the include above. Then we've got int I is 7, int j is 8, int large is not declared yet. I mean, it's not initialized yet. Now we're going to set large equal to, and we're going to call larger, and we're going to pass it the address of I, the address of j, and compare. And then down here we've got compare declared. And by passing it the name of a function, it's kind of like an array name. It's really an address, okay? So it's going to pass it the address of this function. We don't have to have an ampersand because a function is already an address, just like an array is already an address. Which is why on scanf, you have to pass it, if you're passing it integer, you have to pass it the ampersand or the address of the integer. If you're passing it a string is really an array of type characters. And so you're passing an array is always an address. And so you don't put the ampersand in front of it. Same thing here. Its function is always an address, so you don't put an ampersand in front of it. And then it says larger value is, etc. Now here's your compare function. You've got your 2 pointers. And then if the thing at pointer 1 is greater than the thing at pointer 2, we're going to return a 1. Else we're going to return a -1. Okay, and this thing at pointer 1, since pointer 1 is a void pointer, we have to cast it to an int pointer and then dereference it. I would have put parens around that whole thing myself just to make it clearer. Now, if this doesn't make sense, don't worry about it. It's going to be a while before we do anything more with function pointers. And you probably didn't go over function pointers in your C course. If you've had C++, you might have. And then finally in main, we have float F1, float F2, large, and we can call larger. We're going to pass it F1, F2, the addresses, and pass it the pointer to the compare function, and then print. And then the compare is doing floating points here, okay? Our other compare function was doing integers, but this one does floats.